I want you to picture the shop floor. It's, let's say it's 10 a.m. on a Tuesday.
A very specific Tuesday.
Right, yeah. You've got that familiar smell of coolant in the air, the rhythmic hum of the CNCs doing their job. Production is humming along, quotas are being met. Everything just feels controlled.
Yeah, that's the ideal state.
Exactly. And then out of nowhere, you hear it. That piercing metal-on-metal screech coming from one of the high-speed machining centers, it just cuts right through the ambient noise of the shop like a knife.
Oh, it is the sound every operator dreads. It immediately raises your blood pressure.
Right. And the immediate temptation, and I mean, be honest, anyone who has worked a shift has been there, is to grab the earplugs, grit your teeth, and just hope it goes away.
Oh, absolutely.
You think, oh, I can't afford the downtime right now. I'll check it at the shift change. If it's still running, it's fine.
Yeah, that is the classic gamble. We call it that run-to-fail mentality, whether we want to admit it or not. But, and this is crucial, if you're listening to this, you need to know that ignoring that screech is likely the single most expensive decision you'll make all week.
Because that noise isn't just an annoyance, right? Or a sign that the machine is just being grumpy. It's a data point.
It's a scream for help,
Yep.
literally. And that's really our mission today. We are doing a deep dive into the high-speed noise coming from your Machining Center Ballscrew.
Yeah, we've parsed through a whole stack of technical maintenance guides, troubleshooting manuals, and engineering failure analyses to decode exactly what your machine is trying to tell you.
Because looking at this research, the stakes are, well, they're terrifyingly high.
Yeah, we aren't just talking about the operator getting a headache from the noise pollution here. We are talking about critical failure signals.
We are. That noise is the precursor to surface wear, total lubrication failure, or even thermal expansion that is actively warping your machine geometry. If you ignore it, you're looking at poor surface finishes, parts drifting out of tolerance, and eventually the catastrophic endgame.
Which the manuals refer to as screw fracture, or, and this phrase stuck with me, nut detachment.
Yeah.
Nut detachment is a phrase that sounds incredibly violent.
Because it is. It's a genuine safety hazard. We're talking about high-mass components spinning at thousands of RPM suddenly coming apart. It's not just about the machine breaking. It's about it breaking dangerously.
There was one anecdote in the source material that really hammered this home for me. A client described his machine as just singing?
Oh, I read that part.
Yeah, he thought it sounded almost poetic, right? Like it was just working really hard. But the failure analysis showed that by the following week, that singing ball screw had degraded so badly, it was completely undermining the precision of his finished parts.
He was shipping scrap and didn't even know it.
Exactly. And that's really the core theme of this deep dive. We have to reframe how we view the ball screw. It's not just a piston moving things back and forth.
No, it is the heart of the machine's precision. And sound. Sound is your EKG. It's your primary diagnostic tool.
Okay, so let's learn how to read that EKG. If sound is the data, we need to know how to interpret it. The sources identify 4 main culprits behind that high-pitched noise. Where do we even start?
We have to start with the most common offender, lubrication failure. But it's not as simple as asking, did you remember to put oil in?
It usually isn't. The manual's got surprisingly technical about viscosity here. I think the common logic on the floor is, well, if it's making noise, put thicker oil in it.
Cushion the blow.
Right, like putting sawdust in a heavy transmission or something.
Which is exactly the wrong instinct for high-speed applications. The manuals point specifically to viscosity limits. If you are using oil with a viscosity higher than ISO 68, you are actually causing the problem.
Okay, walk me through that. Why does thicker equal noisier and more dangerous when we're going fast?
I would think thick oil creates a better protective film. It comes down to fluid dynamics and shear stress. When that screw is spinning at thousands of RPM, the oil needs to flow instantly to coat the balls in the raceways.
Okay.
If the oil is too thick, think of it like trying to run through molasses versus running through water. It creates massive internal resistance.
So the machine is spending energy just fighting the oil itself.
Precisely. That resistance generates heat due to the sheer friction within the fluid. That struggle to move the fluid actually creates a harsh, friction-based noise. You aren't cushioning the parts, you're overheating them.
So high speed demands low viscosity. That actually makes perfect sense. And I assume the other side of lubrication failure is just dirt.
Contamination, yes. The data is pretty stark here. In dirty environments, which, let's face it, most machine shops, contamination accounts for exactly 30% of all noise issues.
That's nearly a third of all failures just because of housekeeping.
It is. And the mechanism is brutal. Impurities get into the oil, and they basically act like sandpaper. They get trapped between the balls and the raceways. So instead of a smooth rolling motion, you get a grinding motion.
Which leads us directly into culprit number 2, which is mechanical wear. This is basically the aftermath of that sandpaper effect.
Right. If you let that grinding continue, you get something called ball pitting and the peeling of the raceway.
The term peeling really stood out to me in the sources. It sounds like a sunburn, but we're talking about hardened steel. That takes a massive amount of force.
In metallurgy, we often call it spalling. The surface fatigue causes microscopic flakes of steel to literally break loose. The physics of this is fascinating, but incredibly destructive. As that material peels away, the gap between the nut and the screw gets bigger. You lose that tight, preloaded fit.
So now you just have loose parts rattling around in there.
You have clearance, and clearance allows for vibration. Here is the really scary part, that vibration isn't just a symptom, it's an accelerant. The sources state that the vibration from this wear can increase the wear rate by another 20 to 50%.
It's a total feedback loop. The wear causes vibration. The vibration hammers the parts, which causes more wear.
Exactly. And it gets louder and louder until total failure.
Okay, so we have lube and wear. Culprit number 3 feels a bit more human: installation errors.
Yeah, this is often where we see the Monday morning problems. The best way to describe this is that the screw is fighting the machine structure.
Fighting it how? Like it's being forced into a position it doesn't naturally want to be in.
It's all about parallelism. The ball screw has to be perfectly parallel to the guide rails. If it's even slightly crooked, you're forcing the rigid screw to bend with every single rotation.
Like trying to rotate a bent coat hanger.
That's a great visualization. You're introducing a cyclic load that just shouldn't be there. The tolerance here is totally unforgiving. We're talking about bearing concentricity. If it is off by even 0.01 millimeters.
Wait, 0.01 millimeters, that is, I mean, a human hair is roughly 0.05. So we are talking about a fifth of the width of a human hair.
That's all it takes. If you are off by that tiny amount, you are generating significant noise and massive stress on the support bearings. The machine is essentially screaming because it's being physically twisted.
That is wild. Precision really means precision here. All right, bring us home with culprit number 4.
Physical component defects. This is when specific parts of the assembly just give up. It could be a cracked reverser, that's the little tube that circulates the balls back to the start of the nut, or it could be worn dust seals.
And if those parts fail, what actually happens to the balls inside? Do they jam up?
They can jam, or worse, they lose their spacing. If you have missing ball retainers, the balls start hitting each other. Instead of ball, space, ball, you get a ball-on-ball impact.
Ouch. That sounds noisy.
The sources describe it as a metal-on-metal collision. It's distinctive, it's clunky, and it is highly destructive.
Okay, so we've got our 4 culprits: lubrication, wear, installation, and component defects. But here is the practical problem. I'm standing on the shop floor. I hear a noise. I can't see inside the nut. How do I know which one it is? This brings us to my absolute favorite part of the research audio forensics.
This is the real art of the trade, learning the language of the machine.
It really is like being a doctor with a stethoscope. The sources actually break down the difference between a healthy machine and a dying one based entirely on sound. So let's set the scene. What does a healthy ball screw sound like?
A healthy ball screw is boring.
Boring is money.
Boring is perfect. It emits a smooth, continuous, low-frequency hum. Some operators describe it as a soft whooshing sound. It should really just blend right into the background noise of the shop.
Yeah.
If you have to strain to hear it distinct from the motor, that's a very good sign. There's no vibration, and the temperature stays low.
Okay, so a gentle whoosh is the green light. Now let's go through the diagnostic guide for the bad sounds. Let's say I walk by and I hear a high-pitched squeak or a whistle. What is the machine telling me?
That is the sound of dry friction. It's a very sharp, piercing sound. It translates directly to, I am thirsty. It means your grease is dry, deteriorated, or maybe you have that viscosity mismatch we talked about earlier. Metal is rubbing against metal without that protective fluid film.
So if I hear a whistle, I check the lube tank immediately.
Immediately, if you hear a whistle, that is a stop the machine situation.
Yeah.
You're doing irreversible damage every second it runs.
Got it. Whistle means dry. What about a clicking sound, like a click, click, click that speeds up with the RPM?
That indicates a physical internal problem. Think of having a stone stuck in your tire tread. The balls might be jumping or sticking as they move. Or they could be hitting a piece of debris that's blocking the return track. It can also mean the return tubes themselves got dented. It's a mechanical collision sound.
Okay. And the last one. The sources describe this one as scary. A dent rumble. or a heavy hum.
Yeah, this is the worst-case scenario. A deep rumble implies the raceway is peeling apart. That's spalling we discussed. Or the shaft is actually bent, which creates an eccentric load.
An eccentric load meaning it's wobbling as it spins.
Imagine a washing machine with a totally unbalanced load, but spinning at 3,000 RPM. The machine is essentially shaking itself to death. That rumble is the sound of structural integrity failing.
That is terrifying. So just to recap the triage guide, whistling is lubrication. Clicking is internal debris or damage. Rumbling is structural failure.
That's your quick guide. But if your ears aren't enough, or if the shop is just too loud that day, the manuals suggest a manual check. This is a great practical tip for you to use.
Oh, I marked this one down. You disconnect the drive and rotate the nut or screw by hand. But what exactly am I feeling for?
You are looking for the buttery smooth factor. It should be consistent resistance all the way through the travel. If it feels catchy or gritty in certain spots, you're in trouble.
And there's an actual metric for this too, right? For the people who like hard numbers.
Yes. If you feel resistance or binding that is greater than 1 Newton meter, you have a confirmed problem. You shouldn't have to fight the screw to turn it.
There is one more tech-savvy tip in there about the servo load monitor.
This is a great one for the data-driven operators. Check your servo load monitor. If the load fluctuates by more than 15% during a steady move, that is a dead giveaway that the screw is failing, even if the sound isn't deafening yet.
That is great advice. Use the data the machine is already giving you.
Always.
Now, I want to pivot to something that feels a bit more like a phantom. We've talked about obvious physical things like dirt and broken parts, but there's an invisible enemy mentioned in the source material that frankly blew my mind. Thermal expansion.
Ah, yes. This is where physics really comes back to bite you. You could have a perfectly aligned machine at 8 a.m., but by 2 p.m. it's screaming.
And that's just because of heat.
Because of heat. During long machining cycles, friction naturally creates heat. And we all know steel expands when it gets hot.
So the ball screw literally physically gets longer.
It does. And here is the trap. In many precision setups, the bearing supports at both ends of the screw are fixed. They are bolted down solid. This is what engineers call a fixed mounting method. So when that screw expands, it has nowhere to go. It could squeeze between those two fixed points.
So it bows. Like if I take a plastic ruler and push inward on both ends.
It bows, or it simply increases the internal stress in the axial preload. Think of it like a guitar string being over-tightened. The nut becomes way too tight on the screw because the screw is trying to occupy space that simply doesn't exist.
And I'm guessing that tightness just leads to more friction.
Which leads to more heat.
Ah, the vicious cycle.
It's a total thermal runaway effect. The sources mention temperatures can rise to 50, even 80 degrees Celsius inside that mechanism.
80 degrees. That is hot enough to burn your hand.
It is. And that heat does two specific things to destroy your machine. First, it murders your lubrication. Heat thins the oil. It lowers the viscosity way too much. The grease gets thrown out by the centrifugal force because it's too liquid, and the protective film breaks down entirely.
So even if you had the perfect oil to start with, the heat just ruins it.
You cook it. Yeah. The friction coefficient can jump from a smooth 0.001 to a rough 0.01 or higher. That is a massive jump, a 10 times jump right into dry friction territory.
And the second thing the heat does.
Concentricity damage. The heat is rarely perfectly even across the whole screw. The motor end might be hotter than the support end. This causes uneven expansion, which physically bends the shaft. That destroys your concentricity. And now the balls are skipping and jumping inside the nut because the path isn't straight anymore.
It's amazing how fragile these heavy industrial machines actually are when you look at the microscopic physics. A few degrees of temperature can just wreck the geometry.
It really highlights that precision engineering requires precision maintenance. You just can't fight physics.
So we've diagnosed the problem. We know it's screeching, clicking, or rumbling. We know it might be heat. Now we need the cure. The sources lay out a systematic fix. Let's walk the listener through the step-by-step. Step 1 is the flush.
This is critical. Do not just add more oil on top of the bad stuff. That's like putting cologne on a muddy pig. You have to flush the system.
The recommendation is to use low-viscosity oil for this, right?
Yes, specifically under ISO 32. You want something thin that flows almost like water. You loosen the dust seals, inject this thin oil, and move the nut back and forth. You're actively washing out the dirt, the metal shavings, the spalled steel flakes, and the old caked-on grease.
It's a detox for the machine.
Essentially, yes. And only after you've completely flushed it, Do you refill it with the correct ISO 32 to 68 lubricant?
Okay, clean slate. Step 2 is laser alignment.
This goes right back to those installation errors. You cannot eyeball this. You need laser instruments to measure the parallelism to the guide rails.
And we are aiming for that magic number again.
Bearing concentricity must be better than 0.01 millimeters. If it's not, you have to adjust the support seats until it is. There is no shortcut here. If you skip this step, the noise will be back in a week because the screw is still fighting the rails.
Step 3 is preload adjustment. This one sounds tricky.
It requires a really delicate touch. You use a torque wrench to tighten the nut carefully. But you are doing it while actively listening to the noise. You are trying to find that sweet spot, the balance where you have stable resistance, but the noise disappears.
It really is an art form. Now, step 4 is where we get into some hardware upgrades. If the hardware is just shot, or if we want to prevent this in the future, what can we change?
Well, the sources suggest switching to an end cap circulation structure for better smoothness. But the real tech upgrade here, and this is a pro tip for anyone dealing with high speeds, is the balls themselves.
Tell me about the silicon nitride ceramic balls.
This is a fantastic upgrade. Silicon nitride ceramic balls are significantly lighter and much harder than standard steel balls.
Why does lighter matter inside a contained machine?
Centrifugal force. When you are spinning at high RPM, the balls are being thrown outward hard against the return tubes. Heavy steel balls hit hard. That impact creates noise and wear. Ceramic balls have less mass, so they generate far less centrifugal force. They basically glide where steel balls smash.
Oh, I see. So they are more durable and noticeably quieter.
Exactly. They run cooler and quieter. It's a really smart investment if you're running heavy, high-speed cycles.
It's amazing how a simple material change can totally alter the acoustic profile of the machine. And finally, step 5, the environment.
The ultimate preventative measure. If thermal expansion is the invisible enemy, temperature control is your shield. You need to keep the shop temperature controlled at 20 degrees Celsius, plus or minus 2 degrees.
That seems like a really tight range for a big open shop floor, 2 degrees.
It is tight, but it stops thermal expansion before it even starts. If the ambient temperature is stable, the machine geometry stays stable. It's all about minimizing variables.
So to recap the fix for you, flush the system with thin oil, laser align everything to 0.01 millimeters, adjust the preload by ear and torque wrench, consider upgrading to ceramic balls, and keep the room cool.
That is the complete prescription for a healthy machine.
It's thorough, but honestly, when you compare the cost of that maintenance to the cost of a brand new ball screw, or worse, a full week of downtime, it's a no-brainer.
Absolutely. High-speed noise is a warning of accuracy loss. If you address the lubrication, the alignment, and the heat immediately, you protect your production schedule.
It really comes down to the operator, doesn't it?
It does. The difference between a long-lasting machine and a broken one often just comes down to the operator's willingness to listen. You have to prefer that boring hum over the exciting screech.
I love that. Boring is money.
Boring is definitely money in manufacturing. If your shop is exciting, you're probably losing money.
Before we wrap up, I want to leave you with a thought. We spent this whole time talking about how a machine has a voice. It tells us it's in pain through squeaks and rumbles. It tells us it's running hot through microscopic expansion.
It's a constant stream of communication if you're tuned in.
Exactly. So here's the question. If a machine's voice changes based on